Hi everyone, I'm Israel. But this is not about me. I'm here to introduce Minh Quan. Minh Quan was born and raised in Hanoi, Vietnam. He says that his history with math is complicated. Although he appreciated some of his high school teachers, he hated calculus with a burning passion. And it wasn't until he took Calc 2 honors with Professor Sarkis that his interest in math was reignited. He also credits Professor Flappin's Intro to Analysis class with committing him to the math majors. He claims that the trick to his success and mathematical abilities is deferring homeworks to late nights with his pajamas. After all, it got him to college into a company called Analysis Group, which he'll be joining post-grad. Finally, Minh Quan would like to dedicate this talk to his friends, his professors at Pomona, and especially to his high school math teacher, whom he respects deeply and considers to be his second mother. Please help me in welcoming Minh Quan.
Thank you, Israel, for your kind introduction, and thank you everyone for being here today on a fine Friday afternoon. Today I'll be presenting about my senior thesis project, which I have been working for the past year with Professor Sarkis and my team. So it's called Modeling Food Traffic Flow at LAX using Artificial Neural Network. So I would like to begin by talking a little bit about the motivation behind this clinic project. So this is an inaugural clinic between Pomona and the city of Los Angeles. We're working with LAWA, which is the Los Angeles World Airport, and our goal is to use data provided by them to predict a bunch of things about LAX. But here in particular, my project focuses on predicting the customer throughput by at any given time at any terminal at LAX based on their flight schedule. And so since last time, a lot of people have been asking me about the data, so let's talk about the data. This is the data set that we got from LAWA. So we got the flight schedule in and out of Los Angeles Airport. We have Customs and Border Patrol wait times, parking slot status, data from an app called Mobile Passport Control, seat capacity on flights, TSA wait time and throughput, and traffic data. So the data set that I'm running all of my models on is some sort of like time series data in 2018. It's in 1 hour increments. And so since I'm focusing on customer throughput, these are the 3 data sets that I use: flight schedule, seat capacity, and wait time and throughput. So what does the data look like? So this is the box plot of the total customer throughput at Tom Bradley International aggregated by the hour during the day. So you see on the y-axis is the number of customer throughput, and then on the x-axis is the hour during the day. So you can see here the center of this box plots kind of follow this undulation movement. So it kind of increases in the morning, peaking out at around 8 and 9 a.m. before decreasing in the afternoon, and then start to increase again at night around 9 or 10 p.m., which is hardly surprising if you've been to LAX. These are usually the most busy time of the day. And you kind of see very similar pattern in other terminals as well. So for example, Terminal 2, you will also see this undulation movement in the data. Terminal 5, also same. Terminal 6, also similar. Terminal 7, same story. It all goes up in the morning, goes down in the afternoon, and kind of goes up again in the evening. So there are some very similar pattern in all this terminal in terms of customer throughput aggregated by hour. So that gives us some reassurance that our data is not doing something funny that we don't want to, that we need to account for. And so now the question becomes: we have the time series data of the customer throughput. How do we model this? So imagine you have the total throughput of customer on Tom Bradley in January of 2018. It kind of looks like this. How do we model this? Well, we first think of it as a function by playing everyone's favorite game, connecting the dots. And then after this, there are 2 main approaches that we try to use to model that function. So the first approach is using queuing theory. As the name suggests, that is just the theory of of queues. So you build models to predict queue lengths and waiting time in line.
Okay.
And then the other approach is using artificial neural network, which is the approach that I personally use, which is using, so the artificial neural network is kind of like a math model that you can use to predict any real-world function. And the mathematical foundation behind this is a theorem called the universal approximation theorem, which was proven by the mathematician George Sabenko in 1989. So it kind of looks like this, but the gist of it is that you can use the universal approximation theorem to say that you can approximate any continuous function to any degree of precision using an artificial neural network. So hence the name universal approximation. And so that's really assuring because that gives us a theoretical foundation to build upon. And now you might be wondering, what is this mystical neural network? What does it look like? So mathematical neural network is based on a biological neural network. So it kind of looks like a biological system with neurons and nodes. But in the mathematical terms, the neural network kind of looks like this. This is an example of a very basic type of neural network called a feed-forward. So you see there are three main layers. You have the input layer, where you have the input nodes. You have the hidden layer, where you have the hidden nodes. And this is where most of the training happens. And then you have the output layer. So you feed in the input, it outputs something. And if you pay attention, then you see also from the previous talk that this node, each of these nodes in this layer is connected to all the nodes in the next layer through some directed edges. So you see from x1, it goes to all the nodes in the hidden layer, and its edges are weighted. So I will not go too much into how this whole system works, but this is what it looks like. A feed-forward neural net. It's called feed-forward because all the input kind of goes forward in the system. But then this neural network doesn't really suffice because using a feed-forward neural net, we will not be able to apply a lot to our data, which is a very wide range of time series because first of all, feed-forward neural net is very context independent. So think of it as imagine you just arrive at the curbside at LAX departure at say 9 p.m. So you would not really expect yourself at 9:10 to be at the boarding gate, prepared to board the plane. The reason being you will have to pass through check-in counters and then go to TSA checkpoint and so on. So you want a model that can take into account this kind of context. And feed-forward neural net cannot do that. And so we have to resort to a model called long short-term memory networks, or LSTM. So what is LSTM? So LSTM is a special type of neural network. And it kind of looks like this. So this is a beautiful picture taken from a very popular blog post on LSTM. So this is the graph of a repeating module of an LSTM. So it looks like there's a lot going on here, but essentially what you want to pay attention to and what really set this LSTM apart from other models are these nodes right here. So these are called the memory gates. What it does is that it considers the information being fed into the memory. So it will determine whether this information is relevant. If it's relevant, you keep it. If it's irrelevant, you discard it and move on. So this LSTM allows us to retain information from a distant past and use it to predict something a long way into the future. So that's cool. Now let's talk about how we actually build this model. So for our data, we divide it into a training set, 65% of data, validation set, 15%, and then a test set of 20%. The predict feature here is the customer throughput, and we train it on weekday, time, and shifted capacity. Why these variables? So first of all, for weekday and time, weekday is just the day of the week, and time is just the time of the day. So we have a data set that contains the date and time of a very specific date and time, but we cannot train our data on the whole date and time variable. The reason being we do not have enough data to train to train our network on what happens on a specific day at a specific time. So we have to break it down by the day of the week and the time of the day. And then shifted capacity. Why shifted capacity? So capacity is the capacity on the flight aggregated by the hour. The reason why we need to shift this capacity is, if you think about it, if there is a flight departing at noon, then you would expect that there are people on that flight who would arrive at, say, 10 or 11 a.m. in the morning, and so you want to account for the fact that people might arrive early to wait for a flight. So that's the reason behind using shifted capacity. And so now you're probably wondering, LSTM sounds so cool, sounds like something you can just apply to a time series data and get amazing results. So you can just keep training it forever. But then you might want to think twice about it, because then you run into a very common problem in machine learning, which is overfitting the data. So what is overfitting? Overfitting is you're training your data too much. So the data kind of picks up all the noises in your data, and hence it becomes really well in predicting the data it knows, but it lacks generalization, so it cannot predict data that it doesn't know. So this is caused by training the data too much. And then you have underfitting, which is in contrast, you're training the data not well enough. So you just have to keep training data. So how do we strike the right balance? So we want, if we plot the training and validation loss curves on the same curve, so you would want to have training curve to training loss to decrease and validation loss to also decrease. But if you're overfitting the data, at some point the validation loss will shoot up. So you don't want that. You want the validation loss to be stabilized with the training loss. So our method for preventing overfitting is to add an early stopping variable. So essentially what it does is that it tells the neural net that during cross-validation, if after, say, an X number of epochs, the validation loss doesn't increases, then if the neural net doesn't stop improving, then you just tell the neural net to stop validating. And so this is a very popular method of preventing overfitting. And so here's the training versus validation loss curves that we obtained from training our neural net. So you can see here, the orange is the validation loss and the blue is the training loss. You see that this is the kind of graph that we want, because if we're overfitting, then we will see that the orange curve will kind of shoot up after a while, but here it kind of stabilizes, except for Tom Bradley. Something funky is happening there, which I haven't really looked into. And then of course, here are some of the results. So overall, looking at the graphs, what I see is that our model is really good at predicting customer throughput. So you see here on the left is the plot of the best prediction range, and then on the right is the plot of a worst prediction range. So you see that the best prediction on Tom Bradley does really well. Worst prediction is not too bad. And then terminal 1, we also see it's doing okay-ish. Terminal 2, terminal 3, terminal 4, 5, 6, 7. So it's doing really well. But then if I take the same model and use it to predict another variable, which is average wait time in line, then what I see is that this model does not really do well in predicting the average wait time. So you see here, for example, on Tom Bradley, the best one does okay-ish, but the worst one kind of does really, really bad. So right now, our main hypothesis is that the reason for this is that average wait time is not just a function of weekday time and shifted capacity, but it also depends on the efficiency and speed of, say, TSA or Border Patrol staff, which we do not have data on. So that would be something cool to look into. And also for Also, for some reason, when looking at this best and worst prediction range, we see something really interesting, which is most of the extremes, so the best and the worst, usually fall on the end of the year. So usually in November or December. This is just based on the 2018 data that I have. I know Professor Sarkis is something else very interesting. So that kind of like something that I would like to look into too. You know, why is it that this extreme happened at the end of the year? Yeah, and then this is term 6. And of course, am I even a Pomona student if I don't end on 47 slides? So here is the bibliography. And I would welcome any questions you may have.
Thank you.
You mentioned something about training epochs. What does that mean?
Oh, epochs.
Yeah.
So epochs is the number of time you putting your whole data set through a neural network. So that would be once. Yeah. Yes, Isaac.
Something about the model not predicting it properly because you don't have like the sort of time limits.
Yeah.
Is there any way you can like human and your model together? Because I feel like human beings kind of take that into consideration how fast.
Exactly. So that is something that the other team was looking at. So Aurora and Helm and Israel were looking into that. I think they have a fantastic result, but I only was able to look into the known data. Any other questions? Oh yeah.
What software did you use?
So this is so we run this on Python using Keras as a package. Yeah.
TensorFlow? TensorFlow?
Yeah. So Keras is built on TensorFlow. So. Yes, Victor.
How long would the training take?
I run it overnight. So each time, so it really depends on the size of your neural net. So one big part of this project is just trying different parameters and seeing which one works best. So this is a very ad hoc-ish approach. Like you have to try and error. So usually I have to run it overnight for like consecutive days. So yeah, it's very long. Yes.
Did you consider using a feature, a training feature for what like season it is? I imagine summer, for example, has like, I don't know, just a dummy variable for what season it is. Maybe.
Yeah, so that would be really interesting, and I think yes, that is a potential approach. We didn't use that, but since you mentioned season, I think Professor Sarkis had some really interesting result. He was able to predict some sort of like seasonal changes because first of all, he ran the data on the data set from 2017 until now, so he has much more data. But what he was able to show was that in around February, his prediction is way off on the worst range, so it kind of shoots up. And what he hypothesizes is that during that month of February, I think it was this year, there was some sort of like snowstorm happening. So the reason why the prediction was so off was because it doesn't take into account this anomaly. So that's something really, really cool. And I agree, if you have some sort of weather data or seasonal data, that would be something interesting too. Yeah. Alex?
Do you have a lot of missing value in your original data set?
Missing value?
Yeah.
No, I don't think so, because this data was collected and handed to us over by Lava, so there are missing data, but not like over the place. So yes.
How many layers do you have in your network?
So in the final network that I use, I have 3 feed-forward layers stacked on 3 LSTM layers. So what I found is the more you stack layers, the worse it gets because you're overfitting. So you want to strike a balance. Yeah. Any other question?
More questions here? Thank you again.